Thank you. I'm live. Hey, everyone. I'm Steve. This is Dan. We work for Optum. Optum is the services and technology arm of United Health Group. Dan and I both work in an R&D division within the technology group. So we're here today, and we're grateful for the opportunity to talk about ambient computing and computing at the edge. So ambient temperature, ambient noise, ambient light, etc. All of these things have in common the word ambient, which derives from the Latin ambire, to surround us. So it's the light that surrounds us. It's the noise that surrounds us. Ambient computing then is basically computing that surrounds us. Computing that basically happens in the environment, in the background, that the individual doesn't directly manipulate, unlike traditional forms of computing where the object of interaction between the individual and the computing system was the latest shiny PC, or the latest shiny laptop, or the latest shiny mobile phone. In ambient computing, that whole interface, that whole device or set of devices you interact with are invisible. They're no longer front and center in the way the individual thinks about the way they interact with the computing system. So examples of this are, smart speakers, I think, are the best example of this. Essentially, instead of me directly swiping or typing or doing another interaction with, I basically speak into the environment, and I interact with the computing system in that way. Gesture-based interfaces are very similar. We've all seen the movie Minority Report, where Tom Cruise just sort of manipulates things in the cloud. That's another example of ambient computing. Video camera-based monitoring, I think, is also an important one. Again, I don't directly interact with the system, but rather just me moving through my environment is input, and the way I interact with the system, and then analysis on that movement then makes detection on, have I fallen? Have I gotten out of bed this morning? Is my gait changed? That kind of thing. There's other examples of sensors. There's some work that we're doing to just have very simple sensors on the piping, the plumbing within the house, to look for analytics on, how often is the kitchen being used, how often are various appliances within the bathroom being used, and then make inferences about an individual's healthcare journey. Now, some people, Gartner, for example, and others, think that ambient computing somehow represents a new important inflection point within computing. Microsoft CEO Satya Nadella once said that in our industry, big changes in computing platform are correlated with big changes in the way individuals interact with the system. We saw this when we shifted from mainframes and those old, not a lot of you are old enough to remember those big 3270 terminals. I used to work with IBM a long time ago. And now that shifted to personal computing, and that whole way the individual interacted with the computing system changed drastically, which therefore changed the rest of the industry as well. The similar kind of shift between PCs and mobile, the way I use the computing systems changed when my life started to be dictated like this instead of my Apple laptop. And with ambient then, there is enough evidence to suggest that because of that fundamental change in the user interaction modality, that this represents a fundamental game change within the industry itself. As usual in this industry, there's lots of kinds of prognostications. Most of the accurate prognostications are backward looking. So, is this going to happen or not? I don't know, but it's interesting food for thought. Within ambient computing, right, it didn't just sort of come fully formed from the start. In fact, there's several phases that we've undergone, and a lot of them, certainly the earliest phase, is essentially the result of some fundamental research breakthroughs within deep learning. So these are specifically examples of using deep learning so that existing sources of data that were unstructured and therefore not available for computer reasoning suddenly became available. Speech recognition, natural language processing, and video analysis that we've seen lots of examples of throughout this course. So this notion of the basis of a lot of ambient computing is based upon deep learning suddenly making data that was not available before suddenly now available. essentially after that, then we can sort of build different kinds of user experiences based upon those new kinds of data input. So we see a lot of really great activity at the moment with smart speakers and virtual assistants. That's a really interesting application of speech recognition and natural language processing to make a fundamental change in the way we deal with computing systems. Instead of me having to type some full thing, and I've got big fingers and I fat finger a lot of stuff, I can ask Google Assistant or Siri or Alexa, can you remind me when my next doctor's appointment is, or can you help me understand this latest medical explanation of benefits and why I was charged for this and not that, et cetera. And certainly within video-based systems, there's a lot of activity that we're seeing in gait management, just essentially following a person as they walk through their environment, looking for changes in the way they walk that may be indicative of the beginning of osteoarthritis, maybe the beginning of Parkinson's and all that kind of thing. Before, without these breakthroughs, we could not have even imagined of using that kind of analytics because that data was just not available. And essentially the culmination, and we're seeing just some of this starting to suggest, is that we get more truly ambient systems that are much more anticipatory, much more proactive, because they've got this rich set of longitudinal data upon which to do analytics. And we're seeing in many industries, certainly with oil and gas, and we saw references to this at the talk at the beginning of yesterday by GE, the notion of a digital twin, where we now have a sufficient velocity, variety, and volume of data that we can start building these models that are very rich. The term digital twin is often used, and we'll talk a little bit more about that later in this deck. With respect to the team I lead, we're focusing our attention on the intersection between ambient computing, healthcare in the home, and digital health. We think because of the nature of ambient, the nature of smart speakers, the nature of video cameras, et cetera, that there's a sweet spot for our group to focus on, to use some of the breakthroughs in ambient technology and some of the continuing emerging things within ambient computing to help us deliver better digital health solutions, telemedicine, care management systems, proactive condition determination kinds of systems in the home, where the smart speaker is, where the video cameras are, where it's most convenient for our members to receive healthcare, to interact with the healthcare system. Now, that's not saying that that's the only role of ambient computing in healthcare. We've seen some examples of, say, ambient computing outside the healthcare, outside the home itself. There's some great work, for example, in Stanford, where they use anonymized video capture to better understand within an ICU, within a hospital setting, how many of their staff members are actually washing their hands before they enter an ICU room. And because it's all anonymized, we don't know whether Dr. Smith or Nurse Jones didn't wash their hands, but they can get a sense of 90, 95, 99% of their people are washing their hands, and whether or not they need to, do a reminder or, take other measures to address that problem. And certainly, there's lots of other examples where ambient computing is not related to digital health, using smart speakers to answer questions about benefits and scheduling and that kind of thing. But we're focusing on that sweet spot. We're seeing a lot of interesting trends within the industry that ambient healthcare in the home is being inspired by lots of different kinds of market segments. Voice assistants, et cetera, I think that's pretty clear. Just being able to ask questions about one's health is very interesting. Another interesting thing is voices of medical data. I was at a conference recently, and there was a startup in Israel who basically are using just passive listening to the way an individual talks on a smartphone to try to do some prediction of disease. The Israeli company, they really had a good shtick. He said, the stereotypical thing about a Jewish mother, maybe you don't sound so good. Well, basically they're trying to do a Jewish mother as a service, right? They're trying to codify changes in the way I speak longitudinally to suggest maybe onset of Parkinson's, onset of depression, onset of a couple of other disease conditions. We're seeing a lot of also interesting work in smart homes, personal emergency response systems. Most of the vendors, the panic button, I've fallen and I can't get up. They're moving away from that device that you need to actually directly interact with, more towards an ambient kind of solution where they use fall detection on video to be able to say, Mrs. Smith has fallen and she can't get up. Let's interact with the healthcare system and emergency response systems to make sure that we can address that falling situation. In fact, we've got a little bit of an example of that work in our case as well. There's also a lot of interesting ambient work coming from the medical side itself. A lot of very interesting work in sleep monitoring. There's devices, they're both devices within the bed and also some sonar-based devices on the phone, or applications on the phone that are ambient in the sense that I don't interact with them. Well, I'm asleep, so I'm not going to interact with them directly at all. But to help better understand an individual's sleep hygiene, the amount of time they spend in deep sleep, the amount of time they spend in REM sleep, the number of times they're aroused from sleep, and use that to predict better sleep outcomes, and to a lesser extent, potentially predict some medical diagnosis. Idiosyncratic narcolepsy, for example, could be detected there. Talked a little bit about gait monitoring. I think that's a fantastic application of ambient computing as well. And then from the distributed computing environment, there's a lot of interesting work we've seen today at this today and yesterday at this conference about more sophisticated edge computing, more sophisticated AI at the edge. I think that's very important. Certainly for certain cases, emergency response, I think, is a classical one where the latency of doing a detection of the fall, going up to the cloud to actually do that analysis and then do an emergency response, that whole cloud latency, that networking latency, you can't afford in real-time systems like emergency response. All of this in healthcare, I think, is leading to a fundamental shift within healthcare. This particular model, is an example of what I'm trying to illustrate here. Think above the timeline. This is a situation that we've got now, very episodic. So an individual goes to the family doctor, their EMR record gets updated, maybe a couple of tests or scans get run. And then if their health is reasonably good, well, then it's basically crickets between the time they visited and the next time they visit, right? There's not a lot of new information that the healthcare system has about that individual's healthcare journey. Contrast that with the situation where the individual's home has been instrumented with some ambient devices. Maybe the individual has some IoT wellness or fitness wearables. There's suddenly a significantly different variety, velocity, and granularity about data that the healthcare system can have about that individual's healthcare journey. What kinds of things can we do when we go from a situation where it's extremely episodic in the way the healthcare understands about the individual to one that's much more continuous? That's the kind of thing that we're working on here. Now, with ambient, you'll see a fair amount of stuff in the research that talks about the notion of a flywheel, and this certainly applies within healthcare. So consider a situation where aging in place is a really good example of the use of ambient. It's not the only one, but it's a good one, where Mrs. Smith has a choice. Her kids are worried about Mrs. Smith staying in the home. Maybe she's a little bit elderly, maybe she's a little bit frail, and they make a deal with Mrs. Smith. So, Mrs. Smith, I understand that you're not that comfortable with some of these video surveillance tools, a little bit of a privacy concern, but here's the deal. If we can instrument your home that can help us make sure you're okay, then you get to stay in the home, your family gets to be more comfortable, your caregivers get to be more comfortable, that if there is an issue, we can get notified about it. So the idea is that we instrument an individual or an individual's environment and gather data passively. We then integrate that passively gathered data with other healthcare data modalities. And this is an interesting thing about healthcare that's different, say, maybe other industries in ambient, is that the different kinds of data that's available to help understand an individual's journey is really different. We've got electronic medical record data, we've got labs data, we've got claims data, we've got prescriptions data, we've got genomics data, and these are all different ways to think about the individual. Pair that with, say, data coming from the Ambient devices as well as fitness and other IoT wearables within the home, we can then build this database upon which we can essentially start realizing a digital twin, essentially a digital version of that individual's healthcare journey, upon which we can then build better analytics on. We can use those analytics to generate insights, because again, going back to the previous slide, we have this notion of we've got a lot more data coming in at a higher velocity. I don't have a real motivation to rerun deep learning models for inferences if I only get data at a couple of times a year. However, if I get data much more continuously, I have at least the opportunity to generate insights on a more continual basis and then use those insights to trigger action. So maybe, based upon some gait analysis, we're a little bit worried about Mrs. Smith maybe entering a depressive state. We can then have an action to inform our caregivers to say, hey, maybe you need to look at this. Maybe some allied health professionals can help Mrs. Smith get tied in with cognitive behavioral therapy applications on the phone or telemedicine-based group therapy kinds of things. And we can also use that maybe to have the physician recommend that we actually install, that Jewish Mother as a Service example in the environment. That means then we're gathering a different kind of data passively. The digital twin, therefore, is more sophisticated. We could run more sophisticated analytics to get more sophisticated insights about that individual's journey and spin that flywheel so that we can more and more get a much more accurate about an individual's healthcare journey and therefore do a better job of keeping him or her healthy, being earlier to detect these onsets, being earlier to predict things like an emergency room visit, avoid them, which reduces costs and reduces a lot of heartache for the individual as well as the rest of their family. This really calls out for edge computing. A lot of the volume of data, certainly from video and speech recognition, needs to be processed in the individual's environment. So we see a rise of a lot of different kinds of home-based healthcare computing devices that we're looking at, everywhere from something as simple as a smartphone all the way to a very sophisticated and mobile edge computing device. And then we're studying how that relates to how we make that information available within the broader healthcare system. And what we're going to do now is I'm going to pass the baton over to my partner, Dan. He's going to talk a little bit about some of the edge devices that we're working on, and we'll have a couple of little demos. Okay. Dan?
Thank you, Steve. So one of the things that we're looking at is what can we put in a person's home? We talked about all these sensors, all these cameras. Obviously, a lot of those are stationary, but we kind of need more than stationary. We have caregivers come to people's homes, not just to look at them and not interact with them, but they're there to provide, someone to talk to, a reference, an object, something that can help them accomplish tasks if they need it. So we've started looking at in-home robotics platforms to be able to integrate these sensors into a more mobile format within someone's home. So we're currently looking at NVIDIA's Isaac platform. If you've read any of the bullet points, you recognize that a lot of these are very similar to ROS, the robotic operating system. This is NVIDIA's flavor. So it is a node-based system, so you have all your separate nodes you would have one to drive your motors, you would have one to interpret the video from your camera, you would have another to run inference on that. All those nodes communicate with each other in a way that makes them expandable, flexible, reusable, all that sort of stuff. Convenient web interface for monitoring, debugging, all that. But one of the real things here where this stands out from ROS or other robotics platforms is its complete integration with the Unreal Engine. So Unreal Engine, for those who aren't familiar, is a game engine, and game engines are, you might be thinking, what does this have to do with any of this? Well, we can't just put robots out in the world to do things when we haven't tested them. We need a way to test them. And to test them, we have to simulate the environment as accurately as we possibly can. The physics, the dynamics, the visuals, everything that the robot would be seeing in the real world, we need to replicate it as accurately as possible as we can in a virtual environment to get as accurate performance to the real world as we would get from the robot. So as part of the Isaac platform, they include what is called Isaac Sim. An Isaac Sim is exactly that. It's the plugin from the robot into Unreal Engine, where all of the robot's telemetry data is ported directly into the engine. All of the engine data is ported directly back into the robot, the virtual robot. So it's as if it was functioning in the real world. But this is nothing new. ROS has done this. There's a gazebo. Where this really stands out is in the visual space. So let's look at something here called the NVIDIA Material Definition Language. So the idea here is within virtual applications, you have all these different render engines. The render engine is what's responsible for taking your 3D object and turning it into a nice, beautiful picture. But across all of these applications, they have these different render engines that use these different materials. So if I build something in my CAD program and I go to put it into my robot simulator, they're not going to look the same. And that's an issue, because we have all these models out there and we have all these physical objects, and it'd be nice if we could have something tell us what they are without us needing to know what they are. So this material definition language is a standard specification for defining a material so that it looks the same across all applications. So that when I pull a material or an object into my simulated world, it's going to look exactly how it would look within the real world, because the Unreal Engine does a great job of calculating all those lighting physics, the scattering of the rays, all that sort of stuff that makes something look real. So now when we put our virtual robot in the world, we feed that light into our virtual camera, it sees more or less what the real robot would see. So that allows us to do object detection on virtual objects and then port that into the real world and have that recognize those same real world objects just as it did with the virtual objects. But another very cool opportunity that opens up for us is the ability to train object detection models on objects that don't exist or that we don't physically have on hand. So if we're looking at a scenario where we need a couple tens of thousand images of a person, or in this case, maybe we have a very specific help device that we want to be able to recognize in any position, orientation, or angle, we'd have to go around, we'd have to capture a bunch of pictures of that object, we'd have to train a model on them. It's tedious, time-consuming. Whereas now we can just take that 3D model from that supplier, their CAD model that they use to design it, with that material, which is universal now across their design platform and our simulation platform, and we have an object that looks exactly how it looks in the real world. We can orient it digitally, we can simulate lighting conditions, we can simulate occlusion, we can output then those images, those masks, that labeled training data set, tens, hundreds of thousands of images generated on the fly from an object that doesn't actually exist. We train our model on that, and now our robot's able to recognize that in the real world. So it's just a very interesting approach to be able to generate these image data training sets, train on them, and then have that reflect back into real world capabilities. So part of what we're working on here is this Kaya robot. So this is also an NVIDIA platform running on a embedded, this is an NVIDIA Jetson Nano. Let me just disarm it really quickly so we can kind of take a look at what we have it doing. So this is a little, all right, well, my laptop's not working, but that's fine. So this is just a small robot. We have it right now doing a little bit of face detection and tracking recognition. If I could disarm it, you would see it rotating to follow me around. But right now you can kind of hear this tick, and maybe you can see this little yellow camera moving to track my face as I walk around. My laptop died. Well, that's unfortunate. Anyway, so built into this, we have a depth camera, which allows us to see the world in front of us. It allows us to navigate, avoid obstacles, not fall off the edge of the table, things like that. But part of this is that the design files are open source. So we've modified this one a bit. You can see there are a bit of green bits. Anything that's not green is something that we've built, designed. So we've added an additional camera module to it that allows us to track faces. We can point up and down. And we ran into a quick issue there, is that this is a ground-based robot. And if it has a camera that's pointing up at faces, most face detection models are trained on straight-on or profile images of faces, not ones pointing up your nose. So how do we then expand that data set? We need to be able to detect people when we're on the ground looking up at them. So one thing that we can do is we can take that existing data set, we can take those images of marked and labeled faces, we can composite them onto a 3D model of a head, and then we can re-render that from various angles. So now we can then take those images, we can put them back in with our original data set, we can retrain on that, and now we've taken a model that could just recognize faces from the front, and we've trained it to recognize faces from these extreme angles without having to take any more pictures of faces. So it's just kind of an interesting idea of being able to use these virtual simulations of physical objects in order to generate and expand our data sets, so that way we can train on things that we just haven't been able to capture physically. So here's an example use case, as Steve alluded to earlier. So this is fall detection within a member's home. We're using currently a combination of radar and camera sensors to assume a person's location and track their movement. We can detect when they have fallen. We can then dispatch the Kaya, where it can drive over to the person on the floor. It can talk to them using NLP. And from there, we can then decide on how we want to escalate the situation or do anything like that. So here's a little cheesy video that we put together, kind of just to get across the idea of this functionality.
Oh, fantastic.
Brian, do you need assistance?
Yes, help.
I'm calling your emergency contact.
Oh my god, Dad, what's wrong?
What? Chest?
Okay, hold on. I'm calling 911. I'll be right there.
Oh, thanks.
So obviously very quick, very cheesy demo, but this is something that's realistically not outside the realm of possibility right now with given hardware and given technology to drive that hardware. So that more or less wraps up this little example use case, as well as our demo. Does anyone have any questions?
Great. Questions?
See if you can revive it while I field questions. I'll try to handle some of the questions. Any questions? Anyone have aging parents at home?
Oh, there we go. Yeah, so the Kaya should be following me now.
Yeah, but it's not being.
So the Kaya, everything is running on the Kaya itself. It's all on board. The only thing that we're using this computer for is control and monitoring.
So in the fullness of time, with the Kaya acting as a mobile home hub device, Wi-Fi connectivity would be suggested so that it could send signals, 911 calls. It could participate in telemedicine. It could be, the camera there could then be used as a telemedicine kind of thing. So strictly, it wouldn't need to be, but I think pragmatically, to fulfill a role of a mobile home hub device, it would be.
Yeah, so now we just have that base functionality where it's easily tracking us. This is obviously something relatively simple. We're running this in real time directly on the device itself, though. Like I said, the communication is only done for the visual feedback, and so we can send basic commands to it. But otherwise, we're running at about 4 to 5 frames per second at 1280 by 720. We're running through a DNN face detector. We're just using a stock one built into OpenCV right now, so obviously there's a lot of room for optimization here, building these models specifically for these embedded devices and things like that. But we're just trying to build out a basic core set of capabilities right now that we can then slowly build together to provide the functionality as you saw with that example video.
So the face recognition is very important for a lot of aspects of healthcare data. If you remember that slide I showed about, with the timeline and a bunch of little lines coming off of it, one of the concerns in healthcare is how do you know that that data being derived from ambient devices and IoT devices are in fact associated with that individual? In a clinical setting, there's a nurse or a nurse practitioner that's taking my blood pressure, that's taking my temperature, and then he or she can attest that, yes, it was Steve's arm that the blood pressure came from, yes, it was Steve's mouth that the temperature came from. But when you've got IoT data, et cetera, there's an appropriate level of skepticism in the healthcare system. How did I know that that blood pressure data derived from a IoT connected blood pressure cuff was Steve's? With the face recognition, we can start adding some identity attestation so that we could see that the image of Steve, pairing his Bluetooth IoT device, the face recognition said, "Yep, that's Steve. Yep, that's Steve's IoT device. Yep, that's Steve's data." And then downstream, that data packet can be associated with that attestation so that the rest of the healthcare system can, with a high level of certainty, know that that data is legitimate. Other questions? Y'all quiet because we're in between you and lunch?
No, that was a great presentation. Thank you.
Okay, thank you.
Amazing. So